In order to get the force being depicted by an arrow here that pulls the bottle over and makes the pendulum swing out to some angle, we want to look at just a few parameters, and actually this turns out to be fairly simple. Now we're not going to talk about why this works, I'm just going to tell you what works. Later on we'll talk about why, and that's a little more complicated. The parameters we have are the length of the pendulum from wherever it's supported down to the center of the bottle, and the length of the pendulum string down to wherever the meter stick or ruler is by which you're measuring the displacement. We'll also talk about x being the displacement of the pendulum from this point to this point. Now, one thing that we got to keep in mind is that the displacement here is much greater than the displacement you're actually going to experience when you do an experiment. If you're experiencing this much displacement, use a greater mass. Use a 3-liter bottle instead of a 1-liter bottle. If you want to measure smaller forces, use a smaller bottle, or fill the bottle less and put the string at an appropriate point. In any case, the three most important parameters are going to be the mass of the hand here, the mass of the bottle in this case, the position or the distance from the equilibrium position out to the point where the string crosses the ruler or meter stick, and this length here from the ceiling or whatever supporting the pendulum down to the meter stick. If we know those things, then first of all we'll note that the weight of the bottle is just its mass times the acceleration of gravity, because weight is the force exerted by gravity. Since gravity accelerates things at 9.8 meters per second squared, it exerts a force on a mass of m times 9.8 meters per second squared, since the force is a product of mass and acceleration. Then the force that we're seeking, the force down here, which would in the current situation be the force that is stretching the rubber band, or the force actually it's being exerted by the rubber band as it's stretched to pull the bottle back, is simply going to be whatever the weight is here times the ratio x prime over L prime. Remember, those are the distances here and here. So it's simply the ratio of this side of this triangle to this side. You multiply that ratio by the weight and you get the force. That's for small values of x over L, or x prime over L prime. We'll also notice that by similarity triangles, x over L is the same as x prime over L prime, again, if the displacement is small. Now, if x over L or x prime over L prime, doesn't matter, is less or equal to 0.1, the force approximation will be good to within 0.5%. As a quick example, let's focus in. Okay, here's an example. If we have a 1 kilogram mass, and L prime, the distance from the ceiling down to the meter stick or the ruler that's measuring the displacement, is 80 centimeters. X prime, the displacement measured from equilibrium to the point where the string crosses when you're under the force, is 0.4 centimeters. Then the weight is going to be 1 kilogram times 9.8 meters per second squared, or 9.8 newtons. And the force will be 0.4 centimeters over 80 centimeters times 9.8 newtons, 0.049 newtons. So we see that it's really fairly easy with this proportion to calculate forces once we know the mass and therefore the weight of whatever is in the bottle.